Hello guys, so we're going to be covering section 3.5, which is implicit differentiation. So far, we've had functions, of the form like, y is equal to, say, like the cube root of, not the cube root, the fifth root of x squared plus 7. Another one we had, it's a funky looking 7, but, y is equal to sine of x squared times cosine of x. So these right here are functions. You say like, y is equal to like a function of x. That's why we use that notation sometime. In this case, we have, explicit formulas that allow us to find derivatives. But not every function is defined nicely like this. So typically what this is referred to as just like an explicit formula. Say like y, so this like, when we have equations of this form, we usually say these are explicit formulas. Meaning we can, solve for y. Well, in this case, they're already solved for y, but but the thing is that a lot of equations you can get are of implicit form. So an implicit form just means, like they do have a relation, but it's not so easy to get. So we have implicitly defined, curves or functions that can be, defined as a relationship between x and y. So far what I'm saying is just kind of sounds like gibberish at the moment, but when you see what I'm talking about, once I write down an example, you'll see what I mean. So the first one we could have is, x squared plus y squared is equal to 1. Or it could be, x to the fifth y plus 7x y cubed is equal to cosine of xy. So this right here, this right here is a circle. But, we have x's and y's on the same side, and we know that you can't really solve for y and get a unique answer. Same thing with x. Well, I mean, we sort of can, but, we'll touch on that in a second. But this one right here, you can't ever solve for y. There's literally, no virtual way you could solve for that y right there. And because of that, this is, an implicitly defined function or, implicitly defined curve because you can't really, write one in terms of the other. But, we do have some good cases such as, for x squared plus x squared plus y squared is equal to 1. Then we could just, move the x squared over, get 1 minus x squared. Then we do the square root to get, plus or minus the square root of 1 minus x squared. So we get y in terms of x, but we get two solutions for each x. So, 1x gives you 2 y's. Oh. So even then, this is kind of funky. But, this gives us a way to define the unit circle. Maybe instead of actually writing 2, I'll be consistent. I'll say 2 y's. So we could do, if you want to do the unit circle, we'll say this is equal to 1 minus x squared, and we'll say g of x is their other curve, negative 1 minus x squared. What this is going to give us is just the unit circle, radius 1. This will y, this will be x. So this will be, x squared plus y squared is equal to 1. But, if we just look at f of x will be the top piece. If we look at g of x will just be the bottom piece. So let me just kind of mark them better for you guys. Say this one will be f of x, and this will be g of x. So, we can do this and kind of solve for the variables and probably split them up into pieces. In the worst case, and a good case, some cases you can solve explicitly for y, some cases you get many different pieces for y. In this case, we can't really do that. Like, that's not really feasible in this case. So, luckily, we can define curves like that, but we know how to find derivatives with respect to that as well. So, if you remember, like, what we normally do with respect to, like, y with respect to x, we typically want to find, the rate of change of y with respect to x. So typically, what this means is we find the derivative. Like typically we have a function f of x, we take a derivative, we get f prime of x. But when we talk about curves like this, we have dy dx. So, the fact that one is called x and one's called y is not so arbitrary, but the fact is that we want one to depend on the other. Here, when x gives us, a number, we get a y value. So in this case, we can say like y depends on x. And this is how we get that, the dy dx, because that's what we want to find. So typically we solve explicitly for y, but we don't need to do that. So let me just write that. Okay. So what that means is, like, what I wrote was typically solved explicitly for y, but we don't need to really. Like, so, that was typically called like explicit differentiation, because you can explicitly solve for y, and once you take a derivative one side, you just get dy dx. But in the case that we're going to be doing here, we get more complicated things. So what we're going to do here is implicit differentiation. And this will be used for, like, implicit formulas, kind of as you'd expect by the name. I'll say like implicitly defined functions, curves, whatever you want to say, but I typically like to say curves. Because technically, like, a circle, like, you can say y depends on x, and if you want to do like that, you can. But typically, like, this doesn't define a function, because if you look at this x value, you have two y values, so it doesn't pass the vertical line test. So I like to say curves. But, even with respect to the curves, we can still find things such as, like y prime or like dy dx. So just to give a quick idea what we do, we differentiate both sides. So both sides of an equation with respect to x. And the derivative of y is, y prime or dy dx. Oops, with respect to x. So like y prime is equal to, just say like y prime. What this means right here is the action of taking derivative. Or you could say like, d of dx, whatever you want to say. So you'd say like d of dx of y is equal to y prime, or if you want, just dy dx. And then what we do once we, take the derivative of both sides of an equation with respect to x, then we just solve for dy dx. So, so far I've just said a bunch of words. But, let's do an example, as always. So, the first example that we're going to do is, let's do A. If x squared plus y squared is equal to 25, it's a ugly looking 25. 25, we want to find dy dx. I'm going to use, I don't know, blue. I like blue. So the first thing I want to do is differentiate both sides of the equation. So we want to do d of dx of, let's see. No, I don't like blue, but I'll keep this. Of x squared plus y squared, and then d of dx of 25. So this is what it means to differentiate both sides of the equation, and now we just, actually take the derivative. So, we're going to break it up over the sum, so we get d of dx of x squared plus d of dx of y squared, and then derivative of a constant is equal to 0, so equal to 0. So step 2 is actually going to be like what I kind of told you before. So, y is a function of x. So you want to remember that, like typically what you would want to write, just to kind of remind yourself what's going on, is say y is equal to f of x. So that means that the chain rule actually applies. So remember that in this case that we have right here, we have y squared, but remember what you actually have is d of dx of f of x, squared. So when you do the derivative of that, you have to do the chain rule, so you get, f of x, bring down the exponent, subtract by 1, so you get 2 minus 1, which is just 1, and then times by the derivative of the inside to get that f prime of x. So, what this means is, whoops, you need to use a chain rule for, need to use a chain rule d of dx of y squared. Again, because this is basically what's going on. Because we're defining y to be a function of x. So that means whenever you take a derivative, it's going to end up looking similar to that. But instead of writing f of x and f prime of x, we'll write just y and dy dx. All right, so what does this mean? So d of dx, that's just going to be, okay, you know what? Let me actually just show you. So d of dx of y squared is going to equal to, we bring down that exponent, then we just, subtract by 1. We leave the inside the same, because that's what the chain rule is. And then the last way we do is we multiply by the exponent, so dy dx. Well, not multiply the exponent, we multiply by the derivative of the inside, so dy dx. So, you might be asking me, like, why did I take the derivative of y but treat it as x? So it's kind of like the same thing as what we did right here. Whenever you have something defined like this, you basically take a derivative where you treat this as a constant. If you remember what we did previously, we did, u is equal to like f of x. And then whenever we found like, typically what we did first was du dx. So we did, we bring down that, we had d of du of u squared, and that's going to equal to 2 times u, and then du dx. So if you remember that, that's why we basically did, a derivative like this, but with respect to y, but, kind of treating y as just like a normal variable. So, let me just, again, kind of clarify what that means. Because, this stuff at first is a bit weird to talk about. It's a bit weird to work with. But, it just kind of takes a bit of work to really understand, like, the language of everything. So really what we're doing is we have to take a derivative of y, and then we have to multiply by the derivative of the inside. So that's going to be, dy dx. So the derivative, like right here, this is just going to be 2y. And we get times dy dx. And then what we get when we plug it into the last step, remember that this right here is equal to 2x. So I'm just going to write that in black. We get 2x plus, and then the last thing we had was, what we had originally was, d of dx of y squared. That's just going to be 2y times dy dx. And that's going to be equal to 0. Because remember, we had the derivative of the constant on the other side. So the last thing we want to do is solve the equation for dy dx. So, we're just going to divide everything by 2. So we just get x plus y times dy dx is equal to 0. Because, you can just cross out these 2's really. Or divide them out, whichever you want to kind of use your reasoning to justify it. And then lastly, what we do is, just like subtract that x over to get y times dy dx is equal to negative x. And then what that tells us is that, dy dx is equal to negative x divided by y. So far, that's a pretty, weird form of what we've seen before. Typically when we see dy dx, we don't see any x's in there, and that's typically because we have those explicit formulas for y. And, now that we don't have those explicit formulas, we can only really get like implicit forms for some for some derivatives. Sometimes it might work out nicely, but it's not always guaranteed to be the case. So, this was the first part. We want to find is dy dx, but how can we use that to find like an equation of a tangent line? So let's build off of this. Say for part B, I guess. I'm going to find the equation of the tangent line. Say to the circle, the one we were just working with, x squared plus y squared is equal to 25 at the point 3, 4. So remember that we needed to find that m, but in our case is equal to dy dx. But here we said dy dx is equal to negative x over 4. Oops, negative x over y. But, we specify the point. Remember, this is x, this is y. So this is equal to, instead of, it was equal to negative x over y. So it's negative 3 divided by 4. So we get negative 3/4 is equal to our slope. So in terms of the tangent line, what this means is we have y minus y1, so y minus 4 is equal to negative 3/4 x minus x1, so x minus 3. And then, you can just trust me on this. We could just solve for y here, or, I'll just actually do it for you guys. Negative 3x divided by 4 plus 9 divided by 4 plus 4, that's going to be equal to negative 3x over 4. Let's see, 4 times 4 is 16, plus 9 is 25, so plus 25 over 4. All right, perfect. So that's the equation for the tangent line at, of the circle, x squared plus y squared equal to 25 and is equal to 3 over 4. So, this is kind of weird to begin with, but, we can also verify that this works as well. Like, say we want to do like what we did earlier. Instead of just using implicit differentiation, we could just solve for y explicitly and then use those derivatives. So remember, like last time, well, not really last time, but what we did previously was we had, y is equal to the square root, well, plus or minus the square root of 1 minus x squared, and took the derivatives here. And then you just have to be mindful which 3/4 is on. So 3/4 is on, like the upper side, so you have to use the top curve, so the positive one. So 3/4 is on, this piece right here. So if you want to find the tangent line here, all you have to do is take a derivative at this point. So we just get, dy dx is equal to, and this is the same thing as, 1 minus x squared to the 1/2. So we just bring down that 1/2. We still get, let's see, 1 minus x squared on the inside. Now it's again to the 1/2, because it's 1/2 minus 1 is equal to negative 1/2, so the whole thing becomes on the bottom. And then lastly, we have to multiply the derivative of the inside to get negative 2x. And that's just going to equal to, these 2's will cancel. We get negative x over 1 minus x squared to the 1/2. So remember that, m is equal to like y prime evaluated at, x equals to 3. So that's just going to be, negative 3 divided by the square root of 25 minus 9, because that's going to be x squared. So that's just going to be negative 3 divided by the square root of 16, which is equal to negative 3 divided by 4. So it works either way. We could have used implicit differentiation, or we could have just, if we, in the cases that we can't explicitly solve for y, then we could just solve for y and then take a derivative. But sometimes, implicit differentiation is easier to do. Like, if you notice, right here, this right here is equal to our y, so this is the same thing as just negative x over y. And that's kind of where it kind of holds true, kind of one of the ways you could do this. And that's an idea for, later, chapters. Where you'll notice, here's our y, and whenever you have something like this, you could, you can go from implicit differentiation to what you have right here, using the fact that you know what y is. Let's keep going, though. So, we can do another example. You want to find y prime by this implicit differentiation. In this case, it's not going to be that easy. We're not going to be able to solve for y. But it's still going to be it's still going to be feasible. An equation that we're going to have is going to equal to, y is equal to cosine of x is equal to x squared plus the square root of y. So here we'd have to use the product rule. Here we'd have to use the chain rule. Because remember, the thing is that, we're going to treat y like a variable, but it's more of a chain rule. So remember, the chain rule, we treat, I can't believe I just did the tweet so many times. We treat the inside as, just a normal variable. And then we take a derivative of the inside, but our derivative of the inside is equal to dy dx. Or in this case, we're going to be writing y prime instead. Because typically you'll see this prime notation whenever you look at derivatives. It's a very common thing in terms of ODEs if you were going to take that course. So what does this mean? Is let's do, whoops, I hate when that happens. That's going to ruin everything. Okay, delete. Okay. So what that means is, the first thing we need to do is a product rule on the first piece. Oh my lord, what is that going to be? All right, that's annoying already. All right, so the first thing we're going to do is do the product rule on the first piece. So you keep the first one the same, multiply by the derivative of the second piece. So y times cosine of x prime plus, you'll say like y prime, to mean we have to take the derivative, and then cosine of x. And one of the things we should mention is that, interesting, is there just like a space, just like, there's like some space there. Okay, now let's see if that works. Sorry about that, guys. It's like, nope, that's just gonna be there. So in this case, if we just have y, if we take the derivative of just y, we just get y prime. Kind of like what we typically have whenever we have an equation of the form, y is equal to x squared. If we take a derivative here, just get y prime is equal to 2x. In this case, we didn't really have to use a chain rule or anything too complex because the derivative of just y is equal to 1. And then whenever we multiply by the derivative of y, it's just equal to dy dx, or y prime. So we just get, so instead of writing it like that, I'm just going to write y prime. Then we have to do the derivative of the right-hand side with respect to x. We just get 2x. Then remember that we said we have to treat y as a variable, and then, like y is like a function. So we bring down that exponent. So 1/2 times y to the negative 1/2 times y prime. Now what that gives us is, negative y sine of x plus y prime cosine of x is equal to 2x plus, it's going to be y prime divided by 2 square root of y. Now what we're going to do is solve for y prime. Why does he keep doing that? Sorry, I need to figure out these notes app a bit better. If I just hit something, I'll be writing down and my hand will hit something and it'll just immediately jump somewhere else. Okay, so now we're just gonna be solving for y prime. So we're gonna do is move this to the other side, move this over here. Basically put y primes on one side, move everything else to the other. So what we get is y prime cosine of x minus y prime times 2 over square root of y is equal to 2x plus, y sine of x. And let's factor out that y prime to get cosine of x minus 1 over 2 root y is equal to 2x plus y sine of x. Then we're just going to divide by everything right there. We don't really need to simplify it at all. We're going to just leave it like that. So we just get, 2x plus y sine of x, and then divided by the bottom piece. So cosine of x minus 1 over 2 root y. And that's going to be y prime. So in this case, this is the more straightforward method. And the only thing you have to know here is you basically treat y as a variable, or not a variable. You treat y as a function again. So basically it's the same rules. As if y is equal to f of x, where you have to do the chain rule, and you'd have to you have to do the chain rule, you have to take a derivative with respect to it, and all that kind of jazz. And that's why I try to stress, using the chain rule a lot, making sure you know what it means, because it comes up in a lot of places. And this is one of those cases where it shows up. So That example wasn't too hard, and just a kind of quick thing again. Basically just treat y as like a function of x. Let's say f of x. Treat it like that. And that way, whenever you take the derivatives, you get, y, you get, when you typically get f prime of x, then you get y prime. If you had, f of x squared, then you would bring down that exponent, you subtract by 1 on the exponent, and then you would leave the inside the same, so that's why you'd get 2y. Well, that's why you get 2y, and you'd have to multiply the derivative of the inside, so you'd multiply by f prime of x, but that f prime of x is equal to y prime. So you would get 2y, y prime. But, let's do another example. So let's do, x to the fourth plus y to the fourth is equal to 16, and we want to find y double prime. So the first thing we need to find is y prime. All right, so remember that's going to be d of dx of x to the fourth plus y to the fourth is equal to d of dx of 16. I'm just gonna go ahead and take a derivative of everything. So derivative of x to the fourth is gonna be 4x cubed, and plus y to the derivative of y to the fourth with respect to x. So we take a derivative with respect to y first, so we get 4 times y cubed, because again that's basically treating like a constant with respect to the chain rule, or and then we multiply by the derivative of the inside, so times by the y prime equal to 0. And we can just solve for y prime. So these 4's will cancel, and we'll really just get is negative x cubed over y cubed. Because all you have to do is move the x cubed over, divide by it, and then we'll divide by y cubed, and that's what you get. So the next thing I'm going to do is differentiate, with respect to y prime. So we get y double prime is equal to, d of dx of negative x cubed over y cubed. And this is, we're going to have to use the quotient rule. So using the quotient rule, so it's going to be, low d high, so y cubed, y cubed minus high, well no, it's low d high, so times the derivative of negative x cubed. And that's just going to be, negative 3x squared. Then minus high, so, minus x cubed, d low, so times the derivative of the bottom. So that's just going to be, let's see, 3y squared times y prime. And then we're going to have to multiply by, the bottom, so y to the 6. Well, not multiply, but it's going to be, over low squared, so y cubed squared, so that's just y to the 6th. And this is, again, just to kind of clarify, this is d of dx of negative x cubed. And this right here is d of dx of y cubed. So let's go ahead and simplify. So we just get, negative 3x squared, y cubed minus, plus actually, because, minus are here, so plus. It's going to be 3y squared, actually let me keep it together, so 3x cubed y squared y prime divided by y to the 6th. But remember what y prime was earlier, was that remember we solved for y prime, we actually know what it is. So y prime is equal to negative x cubed over y cubed. So we can substitute that back in. what we get is negative 3x squared y cubed plus 3x squared times negative x cubed divided by y cubed. All this is also... Okay, that was 3x cubed times y squared times all this, divided by y to the 6th. And then let's go ahead and simplify a bit. So that's going to be negative 3x squared y cubed plus 3x, well, now it's going to be 3x to the 6th, negative 3x to the 6th. Because here it's negative, here's a third, so add them together, then you get that, negative 6. Well, you get to the 6th exponent of, you get x to the 6th. Hate just so how much all this math is just so many words. But you just get y squared divided by y cubed, so that's just going to be over y. And then all over y to the 6th. What you can do is just multiply by y, on the top and bottom to get rid of that y. So you get negative 3x squared y to the 4th minus 3x to the 6th divided by y to the 7th. That's going to be our y prime. So, a lot of this was a lot of algebra. It's a lot of derivatives. And it gets a bit complex, especially in this scenario, but, we can keep on moving on. Then one last section we have to do is, on this section is, derivatives of inverse trigonometric functions. So let me write that down. So we know derivatives of, we know the derivatives of sine of x, cosine of x, tangent of x, and a lot of the trigonometric functions. We already know what the derivatives are. So remember, recall that, if y is equal to arc sine of x, then, y, we have cosine, sine of y is equal to x, and this is for, y is between negative pi over 2 and pi over 2. So if we want to find y prime, this might be easier, we don't know what the derivative is, so we'll put a question mark around there, but we can use this, but, sine of y itself, we can be used to solve for y prime. And as you can guess, as we kind of been doing in this chapter, using, implicit differentiation. So, let's take a derivative of sine of x is equal to x using, with respect to x. So more d of dx of, sine of y is equal to, d of dx of x. So we just get cosine of y times y prime is equal to 1. So that tells us that, y prime is equal to 1 divided by cosine of y. But, this doesn't actually give us a derivative in terms of x, but we can use, the fact that x is equal to sine of y. And then use our Pythagorean identity. So, since y is between, negative pi over 2 and pi over 2, and then we have that cosine of y is positive. In this scenario situation, I guess. I always say my brain likes to mix up two words. I think it's like kind of similar to spoonerisms. So the fact is that this is where our y is. One second. Something was going off in my room. Okay, so let me just kind of go over the setup again. Here we want to find what, here we define y is equal to arcsine of x. And we know that, because of just like how these functions are defined, especially in inverse functions, is that it tells us that, y has to be between negative pi over 2 and pi over 2. And also that we get, x is equal to sine of y. So when we found y prime, what we got was, 1 divided by cosine of y. But again, kind of the fact that, y itself is like an inverse function of arcsine. So what we have to get is that, y is between negative pi over 2 and pi over 2. And that's just one of the restrictions. If you look at the graph of arcsine of y, you should be able to see that, you basically should see it's squeezed between those values. So, now that we know this, we know that we'd actually do some algebra with this. So we get that, cosine squared of y plus sine squared of y is equal to 1. So the algebra they're going to be doing is on this expression right here. So we know this is true. This is going to be true for all y. Y is between negative pi over 2 and pi over 2, so this is pretty nice. So then we can use this expression to solve for, cosine squared of y. So it's going to be equal to 1 minus sine squared of y. Then we can take the square root of both sides is equal to 1 minus sine squared of y. Remember, this is plus or minus, but this right here implies that cosine is, greater than or equal to 0, so we're just going to drop that negative one because that's not the one we need. And then lastly, if you remember what I said earlier, that we could, basically solve for y. Not like solve for y, but we could replace things that we know with something else. We know that sine of y is equal to x. So this right here will become the square root of 1 minus x squared. So now what we can do is plug it into this form. So we get, 1 minus x squared, the 1 divided by the square root of 1 minus x squared. So, to make it clear, we get dy dx of arcsine of x freaking YouTube notification. So the derivative of arcsine of x is equal to 1 divided by the square root of 1 minus x squared. So you can actually do this with a lot of other functions as well, and you can verify this. And that, you can do it with a lot of the other, derivatives of other inverse trig functions. So I'm just going to list them out for you. And you're welcome to, verify these. And honestly, it'd be good practice to at least check 1 or 2 of them to make sure you know how to do it. Because, a lot of times you might struggle remembering how to do these, or just remembering what these are. And a lot of times you can remember by just seeing something a lot, but it's easier to remember something if you just actually do it. So, what we said of d of dx of arcsine of x, that's just equal to 1 divided by the square root of 1 minus x squared. D of dx of, arc cosine of x. That's going to be pretty similar, but instead of positive, now it's going to be the negative. So now the negative square root of 1 minus x squared. Negative d of dx of arctangent of x. That's just going to be 1 divided by 1 plus x squared. And now we have, the reciprocal functions, so like arc cosecant. So arc, cosecant. That's going to be equal to -1 divided by x square root of x squared minus 1 d of dx of arc secant of x. That's just going to be equal to 1. Well, basically the same thing, but now it's going to be positive x squared minus 1. Then lastly, d of dx of arc tangent. Well, arc cotangent. So it's just going to equal to -1 divided by 1 plus x squared. So, let me just double check. Yep, that's it for this section. So, that's it for 3.5, I think. Yes. And, again, it's not like too bad or anything. It's just like a bit weird at first to get used to, especially with all this, like, now you're taking derivatives in another new way. And that's honestly like half of calculus. Calculus is just like learning how to do something entirely new. And so, like, doing these isn't so bad, but the main thing here is knowing what implicit differentiation is. Because implicit differentiation is basically just like treating y as a function of x and just using the chain rule, basically. So, like, try if you're having a bit of issues just understanding this real quick. I mean, or not real quick, but understanding this so far, like, try not to worry about it too much because it just takes a bit of practice, especially just like knowing what the ideas are, knowing what we're doing with y, why we're treating it as like a variable. Well, really we were treating y as like a function of x. So when we did, like the chain rule with like, f of u is equal to like, you could say like y is equal to f of u, then u is equal to like, g of x. That's basically what we're doing. We're doing stuff with that u instead. And, which can be pretty annoying at first, but, you guys got this. We get into more complicated stuff in the next section, but try not to worry about it too much. But that's it for this video. Like, comment, and subscribe, I guess. Let me know what you guys think about this section. If you have any issues, feel free to email me as always. I'll try to help out. And again, for the last section, try to verify, I don't know, like, see if you could verify this one or here, and then maybe this one. If you can verify those, then that'd be pretty awesome. And if you can do those, then I feel like you would have a really good understanding of, like, some of these derivatives. But okay, that's it though. Peace out, guys.